Hello everyone, my name is Quốc Bảo, and today I'm going to present the work Rosette Transnet++, a novel deep neural network for sophisticated cardiac segmentation. So our research project focuses on transforming the 2D medical images into the 3D representations for better observation and analysis. So this requires that the 2D segmentation output must be highly accurate, or we need to achieve the near perfect accuracy. Recent state-of-the-art models are only benchmarked on the simple cardiac datasets on the right side, you can see. However, ironically, it's not applicable when performing segmentation on those datasets. And with the more sophisticated cardiac datasets, featuring very detailed and more intricate annotation, but they are not benchmarked on these datasets. Current works are divided into two groups, the CNN-based networks and the transformer-based networks. The CNN-based approaches shows limitation in capturing the long-range dependencies or global modeling context, while transformer-based approaches exhibit promising results, but both types of networks perform poorly on a complex cardiac data due to their inability to capture the interslide information with interslide information. And they perform the segmentation in a slide-by-slide manner. Therefore, the information between multiple sources are totally ignored and not aggregated effectively. Those problems can be solved with 3D neural networks like UNet3D or VNet, but they require highly computational cost and, of course, inapplicable in practical clinical settings. Recent research tried to decompose the 3D networks into two streams. The first stream to capture the spatial information, the interslide information, and the second stream capture the interslide information, and then those information are fused together. We also took the inspiration from those research, and because it stimulates how the visual cortex and retina of human work. And this is our approach, our proposed architecture. In the encoder of our architecture, there's a multi-scale feature extraction with nested skip connection, and it will go through the linear embedding and positional embedding. The transformer layer will capture the interslide information, the spatial information, and our proposed module, rotatory attention mechanism on the right side, the second stream, will capture the interslide information, the interslide connectivity, and those two information are fused together by the additional operation. And they are talking more about our rotatory attention mechanism, the second stream. It can capture the information between many slices. Consider we have three slices, the left target and the right, or the previous, the bottom, the center, and the top. We first compute the representation for the left and the right, and then aggregated the information from adjacent slices into the target slide by the single attention module over here. So this is the mathematical formula of single attention module. We can discuss more about the implementation in the poster sessions. We benchmarked 9 models, of course, including our method, across 4 medical datasets. And we reported 3 main metrics, DAS score, IU, and hospital distance. Clearly, our method outperformed and has proven superiority over other methods across all cardiac datasets except for the synapse dataset, which is the abdominal dataset. In the data analysis, we conclude that this limitation can be maybe due to the discontinuous nature, the discontinuity in the data of synapse. Furthermore, our method is more lightweight because we only need very few transformer layers, especially 4. The training graph, our model converged pretty fast. The visualization of class-wide score across multiple datasets. This is the visualization, the comparison between our method with TransUnet, representing the transformer-based approaches, and the UNet plus attention, representing the CNN-based approaches. Clearly, we can achieve near-perfect accuracy of segmentation and reconstruction in 3D. And you can also notice the spraying phenomenon. I call this the spraying phenomenon when there's a confusion between differentiating cardiac and non-cardiac details. We also conducted an application study of our rotatory attention mechanism. The performance significantly drops when no rotatory attention mechanism is applied across 4 metrics, and you can see over here. And this is a 3D visualization of our application study on rotatory attention mechanism. There's a spraying phenomenon. We also visualize the interaction between many high similarity batches. You can clearly see the difference. We also want to interpret how our models act, how our model performs. We adapt the GradCam for the segmentation task. To analyze the specific regions that model focuses on during inference. We want to know what the model sees during the inference. And without a rotatory attention mechanism, our model is confused by a lot of regions, including the redundant and irrelevant parts. It is actually confused where to look at. However, with the rotatory attention mechanism, the distraction is totally excluded. Our model can focus on the most relevant part, therefore produce the very good segmentation result. Thank you for listening.